So this probably doesn't affect people here, but we had a slight streaming problem, so it takes a while for them to set up the live streaming for online for people attending online. So I'm just going to check whether they can see us here. Okay, it looks like this time we will be having a live lecture for the online participants. Great. Okay, so hope everybody had a great weekend. A couple of things to announce for week 2. So today we're going to talk about data definition language. So in SQL there are 3 types of languages: data definition language, data manipulation language, as well as data control language. So today we're going to review how to map the ER diagrams into SQL, and then in the meantime we'll talk about data definition language, and you'll see more of that in the practical exercise for this week. And so tutorials start this week, so we'll have a lot of experienced tutors to help you with not only in terms of concepts as well as practical stuff. So if you cannot install PostgreSQL on your computer via VLab, then you need to get on it very quickly. Because right now, last time I checked, let me run that again. No. Let me see how many people we got. Wait. So right now we only have like 276 people who have logged into VXDB. So every time if you log in here, it will create folder named after your ZID. So we can see that 276 people have successfully logged in here and set up PostgreSQL. So about half of people, like probably maybe they are from the online string and they didn't know about it. So if you haven't done it already, please watch the practical 1 exercise. So I released a video about it last week. If you haven't done it already, please do that, because everything in this course depends on you being able to log into this server and you can play with PostgreSQL. And quiz is due this Friday night. Quizzes are usually not super hard if you watch the lectures. And the assignment 1 will be out by the end of this week. So the assignment this week, the assignment will be about data definition, data control languages, and we will actually see the example of the database in assignment 1 on Thursday. So on Thursday, we're going to give you a preview of the database we'll play with in assignment 1. And hopefully by the end of the week, probably on Friday, we're going to release assignment 1. And assignment 1 will be due in week 5. So you get like at least 2 weeks to work on it. And for people who are sending us emails, so it is best, because now we have a bunch of different contexts. It's very important for us to understand like what you're talking about. So if you're Linux, if you see a $sign, then you're in Linux. If you have like DB in front of you, then you're probably in the PostgreSQL shell. And for people who have done other CS courses, this is probably a no-brainer for you. But we also have students from other courses taking this, other majors taking this course as an elective. And for those people, this is very important for you. So you need to understand the basics in Linux, and you need to understand when you're in Linux and when you're actually in PostgreSQL. And if you're in Vim, you're doomed. No. So Vim is not a, some people say Vim is not a beginner-friendly text editor, but we have a couple of other text editors in our teaching server. You can use Gadget, you can use Nano, you can use Vim, And I think you can even use VS Code from if you use the VLab interface. So one thing I love about UNSW CSE is that you guys have one of the best teaching facilities here. So one thing great about this university and one thing great about this course is that they have actually allocated a lot of resources for you to use. So for people who have taken CS courses here, you probably know that we have labs. So we have all kinds of labs. We have labs in this building. We have labs in K17, J17, as well as K14. So we have a large number of labs. You can just go in there, log in, and then and then it will be exactly this interface, but it will be a lot better if you join it using the lab instead of joining through browser here. But now I have no choice because I have to demonstrate, so I'll join through a browser. So for those who don't know, I recommend you. So there's a student asking me, what are your suggestions for do well in this course? Well, my suggestion is stay in the lab, right? Stay in the lab more often, and then actually use Linux, use PostgreSQL, stay there and implement something, write some SQL code. So that's the best. That's my best advice for if you want to do well in this course, because a large component of this course is like on the practical aspect. You'll be tested on that in the final exam as well. Okay, that's enough housekeeping. Is there anything else I need to talk about? Okay, great. Okay, let's get back into ER diagrams. So we're going to briefly review how to map ER diagrams into SQL. So ER diagrams, hopefully you remember from last week, we have entities, relationships, and attributes. So basically entities are all of the nouns. Relationships are describing the interactions of these entities, and attributes are describing properties of these entities or relationships. And when we are designing the ER diagram, a couple of things we need to be aware of is we always, so entities are super important. When we are converting them into SQL, we create a separate table for it. For relationships, do we always create tables for them? What do we look for? Pardon? Yeah, and can you specify like when we use foreign keys instead of creating a new, like we will always use foreign keys no matter whether we create a new table or not, but can you specify when do we need to create a new table and when do we don't need to create? Pardon? Yeah, exactly. So the good thing about ER diagrams mapping to SQL is that when you're in doubt, you don't get penalized, or you're technically correct for creating a new table for every new relationship you see, for every weak entity you see, for every multi-valued attribute you see. But to make things, usually what we do is that when the relationship is many-to-many, we need to create a new table for it. And then for this table, the primary key will be the combination of the primary keys from those participating entities. And when we have a one-to-one relationship or when we have a one-to-many relationship, we don't bother creating a new table because we can get away with storing the primary key of one entity in the other entity's table. So we'll demonstrate that in more examples. And for attributes, so attributes are the easiest part in this ER to SQL mapping, because the only thing hard about attributes is that you might need to create a new table for multi-valued attributes, and you might need to flatten the composite attributes into smaller atomic attributes. So basically, all entities are mapped to tables, relationships are mapped to tables or foreign keys, and multi-valued attributes, weak entities, and subclasses, most likely we're going to create a new table for it. And last time we stopped in a place where we were just going to talk about how to map subclasses into SQL. And that's actually a tricky part, and it's not super important for this course, but we're going to talk about that in the end after we give a couple of more examples. So this is the data definition language that we talked about. So basically, with data definition language, we can create tables in SQL, and then so tables together, we call a series or a collection of tables a schema. A schema is basically the data, the information about the data you put in. So it is data about data. So one table here is just a table. So if you have a collection of tables, we call it a schema. So in this course, in the assignment, if we say the schema is this or schema is that, then we're talking about a collection of create table statements. There are some built-in types, so hopefully you get to experience more of this in the practical 2 exercise. And there are some built-in types. There are integers, numeric, and real. And for text-related, you can define the length of the string. And for time, you can define date, time, timestamp, and time interval. And we also have Boolean. So personally, I don't memorize any of these. So what you can do is that the recommended way of using this syntax is not to memorize them, but to open up the PostgreSQL menu. So the recommended way of learning SQL is that you open up the PostgreSQL menu on the side, and then when you're coding, you can refer to the menu to select the correct syntax. And if you use a syntax often enough, then you'll remember it. So, and most of the times we're using like very simple, yeah, sure. Pardon? What does the bracket n mean? Bracket n. Oh, so bracket n basically defines the length of the field. So char n is basically means that you're allowed to type n characters in this field, and varchar is you can type at most n characters in this field. So it's basically a length constraint. For varchar and so char, you need to so char is like it has to be a fixed string. So like for TFN, we always have like 9 characters, exactly 9 characters. But for varchar, is more used for name and like first name, last name, where the range can differ. Like my name is longer, your name is shorter, but it specifies the longest possible constraint. And for text, it's just you can treat it as a string literal. So you don't specify anything about that, and just a string literal. And yeah, so that's a good question. So as you can see that we'll need to select different types of type for different types for different attributes. So if it's like a TFN or if it's like a ZID where the length is fixed, then we can go ahead and declare it char 9 or char 12 or something. And for names and for address and for things like that, we don't know the fixed length of that string, so we put a max number of characters allowed in there in case people have different people's address and people's names have different lengths. And also you can create your own types. So you can use create domain, create type to create your own types, but most of the times we can the built-in types are enough for us. And constraints are more important because constraints are actually more related to the business logic that we try to impose. So a lot of times, I think last time we demonstrated the case where we might want to make people's age larger than 0. We might want to make people's salary not negative, things like that. For all of these constraints, we can implement using a check constraint syntax. And usually there are two types of constraints that we want to implement: the primary key constraints, the foreign key constraints. So these are the key constraints, and these are domain-specific constraints that we want to, for integers, for text, and these are the domain-specific constraints we want to impose on the schema. And I have made a video about that in the practical exercise 2, so I'm going to release that after this course. So let's just get some idea of how we actually implement these constraints. So these are some widely used constraints in business logic. Sometimes we want positive integers, sometimes we want marks. So obviously you can declare something as integer, but if you don't impose any constraint to it, then people can enter bad data. So they can put -2, they can put 102, then it's not a valid mark anymore. And for UNSW course code, obviously we use the convention of 4 uppercase letters followed by 4 digits. And for term codes, we have a fixed pattern as well. For student ID, we have a fixed pattern as well, and so on and so forth. So for things like positive integers and marks being in the range of 0 and 100, these are fairly easy. So you can just do a very simple, you can just check age larger than 0, or you can check marks between 0 and 100. And for more advanced pattern matching, like you need to, like for UNSW course code, you got 4 upper class letters followed by 4 digits. And for term codes, you have 2 digits followed by 1 upper class letter and then followed by 1 digit. For things like this, we need more powerful pattern matching. So you can read more about that in PostgreSQL Manual Chapter 5 and Chapter 9. So we have a bunch of operators dedicated for this. You can use the like operator, you can use a similar to operator, and personally I like to use the tilde operator because it allows me to use regular expression. And regular expression is one of the most beautiful things in computer science. And so these are some examples of how you can impose these constraints. So one thing that I want to comment on these examples is that these are, due to space limitations, we're implementing these constraints in line. So right after you define the attribute, you can put check the value, something like that. So you can put the check constraint right after you define the attribute. But in real implementation, sometimes it gets really messy, so we put the check constraint in the end, just like we can do, and we can do the same for primary key constraints as well as foreign key constraints. So for positive integers and marks between 0 and 100s, these are pretty straightforward. We can basically check the value. So value is the actual attribute here. The value is larger than 0. And we can actually check the mark is between 0 and 100. And for more complex pattern matching, you can use similar to, and so basically it will compare the text on the left-hand side to the regular expression, to the pattern defined by a regular expression on the right-hand side. And for people who don't know regular expression, I can give you some ideas. So everything in here is the allowed characters, and in curly bracket, it defines the number of such characters. So basically, this means we need 4 upper letters. And here, 0 to 9 basically means we need a digit here. And then 4 means we need 4 digits. So basically, this pattern can be described as 4 uppercase letters, like here, and then 4 digits. And if you want to, and for UNSW term code, because we know the third character is going to be uppercase T, so we just put T there. So basically, we need T as the third character, and before that we need two digits, and after that we need exactly 1 digit. So these are exact matches. So if you give 26 lowercase t and then followed by 1, then this match will fail. So it's up to you whether you design it to be case insensitive or case sensitive. So if you want to make it case insensitive, you can put lowercase t as well as uppercase t in the bracket. And for student ID, you start with a lowercase z and followed by 7 digits. Is that only 7 digits? Yeah, 7 digits. And so basically, you can, if you haven't learned regular expressions in other courses, please go ahead and do that. That will be super useful in this course, not only in this course, but also in other computer science courses in general. And there's another thing that we can use is we can check whether your value is in a predefined range of values. So, and these are mutually exclusive. So if you want to say we only allow color in red, green, or blue, so color has to be one of these values. So these are exclusive. And same thing with grade, we can impose that grade takes after one of these values. So it cannot take after HD and D at the same time. It needs to take after one of these values. And this will be slightly useful when we are trying to map the subclasses. Any questions at this point? Yeah.
You combine them.
Pardon?
You combine two of them.
Can you combine two checks? Yeah.
So this is like between 0 and 100. I would imagine n is like the keyword to combine to like.
Oh yeah, exactly. That's a very good question. So here, because we have a keyword between for things like this, so you can say check mark larger than or equal to 0, and then end mark less than or equal to 100. So basically, you can concatenate more conditionals together, just as in other programming languages, and you can also use OR as well. And let's do another exercise for ER to SQL mapping. So this is I think this is something we looked at last time as well. So this is a student enrollment database. This is the ER diagram. And just by looking at it, how many tables do you think we should create for this ER diagram if we're mapping it to SQL? 3, which are student, course, school. And what about like relationships? How do we represent relationships in this case? Yeah, we definitely need three tables for the 3 strong entities. What about the relationships? Like how many more tables do we need? I think you know the answer. Pardon? Yeah, and is that it? Yeah, exactly. So for enroll, that's a very good answer. So I think you get it. So for enrollment offered by their 2 relationships, and if we're lazy, we can just create an enrollment table, which stores the course reference for student ZID as well as the course's primary key. So course primary key is slightly more complex because it has 2 components, but either way, we'll need to grab those primary keys in that enrollment table. And for offered by table, if we're being lazy, we can also create a new course reference new table. But we notice that this is a many-to-one relationship. Well, it depends on how you look at it. If you look at from top to bottom, it's many-to-one. If you look at from bottom to up, then it's one-to-many. So basically, on the school side, because there's an arrow pointing towards it, then school is the one side and course is the many side, which means that one school corresponds to many courses. So, and course has total participation, which means that a course needs to be offered by exactly one school, whereas a school may not hold any course. So in this case, this is a one-to-many relationship. It makes sense for us to store the information about school in the course table, because for each course, we can basically store the primary key of the school, and it doesn't make sense for us to ask the school table to store all of the courses it will run, because that would be a disaster. So for COMP3311, we can store that we are offered by school CSE. Yeah.
What if it's a many-to-many relationship? What if each course can be offered by many schools? Would you create a new table?
Yeah, exactly. In that case, I'll create a new table. So in that case, it is exactly the same scenario with enrollment, where you have many things on the left-hand side, many things on the right-hand side, and then imagine if you connected lines, whenever there is a interaction, then you have a nice bipartite graph. And to represent this nice bipartite graph, we'll need a cross-reference table. And the reason why we don't use that when we have a one-to-many relationship or one-to-one relationship, imagine if we have like one-to-many relationship, then the bipartite graph, the one side of the bipartite graph collapses to just one node, and on the right-hand side we have like n nodes. So basically it becomes a star. And in this star, we can ask the entities on the many side to store information about the star node, instead of creating a cross-reference table to actually store this very complex bipartite graph. And if you don't know what that means, it's totally okay. But if you don't know what that means, yeah. If you don't know what that means, you can try to put all of the instances of students on the left-hand side, instances of students on the right-hand side represented by a node, and whenever a student enrolls in a course, you connect the dots, and then you end up with a very complex bipartite graphs. And usually the way we present such bipartite graphs is using the cross-reference table, and that's why we need to create a new table for it. Yeah.
It's a very common operation to query which courses are offered by a school. Is it like faster to do it using another table so you can do it backwards? Because if you want to find out which school has how many courses, you want to list all the courses the school has, and you have to search through the entire course table. Right? So is it better if that's a very common query, is it better to do it using another table?
That's a very good point, because you mentioned the database design and what we actually query. So so can you repeat the query? The query is okay. So if you want to make this query faster, for instance, list all of the courses offered by a school, and you're asking whether it is more efficient to use the cross-reference table, right? In that case, it can be faster because you don't need to join anymore. So basically, if you don't do that, you need to join these two tables together, and it will be exactly the cross-reference table that we would have made otherwise. So if that is very common operation, like we want to count the number of courses in CSE, we want to know exactly which courses are offered by CSE, then if we had a cross-reference table of the two, we can just query that table. That will be slightly faster. Yeah. So, but I like his way of thinking. A lot of times, there's no right and wrong in the schema design, and it has a lot to do with, it also has a lot to do with the type of query you anticipate. And we'll talk more about that in whether we should model something as a multi-valued attribute, or whether we should model it as a man-to-man relationship. And you recognize that both of these are modeled as a separate table. But sometimes we choose to model it at multi-valued attributes, but sometimes we choose to model it as a man-to-man relationship. So think about that in back of your head, and maybe we'll talk about that later. So just as you guys have figured out, for entities, we need 3 good tables. And for one-to-many relationship, we don't need a new table. We just modify on one side of the relationship. Specifically, we modify the n-sides table. And in this case, this is course, school, and course is the n side, and school is the one side. And we need to store the primary key of the school as the foreign key in the course table. So for all the other stuff, it's not very interesting. So code is the text, term is the text, and this part is interesting because to uniquely identify a course, the primary key is code combined with term. So for instance, in this course, the primary key should be COMP3311-W2-Monday-26T1 term 1. So that uniquely identify a course offering. And because we need to model the one-to-many relationship offered by, we need to throw in the foreign key. So basically, for each course, we need to store which school it is offered by. But when we are entering this information in the database, they get confused, like where is school coming from? Well, the school is actually coming from the primary key of the school table. And for the school, the primary key is name. So basically, in this table, we're storing the school's name. So another thing about this primary key is that this new variable or attribute, you don't have to name it. Like, you get to name this attribute. So you can name it school name, you can name it school, or you can name it name of school. So this is up to you. But you need to impose that this is a foreign key which references school's name. So hope you get that. And for the man-to-man relationship, we don't have any other choice but to model it as a separate table. So in this table, it looks kind of messy here. I'll explain line by line. So basically, for enrollment, remember that enrollment is a man-to-man relationship between student and course. So how do we uniquely identify an enrollment? For instance, your enrollment in this course. How do we find your mark in this course? So mark is a relationship-specific attribute. So this attribute is queried a lot because in week 11, we will need to find out your marks. So how do we uniquely identify this piece of information? Well, we need to know who you are, and we need to know which course you're taking. So who you are is identified by your student ID, and which course you're taking, which course you are taking is identified by the course code as well as a term. Yeah, exactly.
I don't understand why you need an enrollment table. Like all this table represented in the student table in the course table itself. Right?
So you don't understand why we need a separate table, right? So you're saying we can store this information in student and course?
Yeah.
How do you think we should do? I mean, we can do that, like in some way, but how do you think how do you propose to do that?
In the student, we can have a field called enroll in and the current term, and the term, corresponding term. And the enrollment will have the course name and the term, the student took the course name.
But the thing with this relationship, as you can see, that this is a man-to-man relationship, right? So as you're one of the students, so you'll be taking many courses, for instance, like 5 courses. And how do you plan to store 5 courses in one row?
So for every term I'm enrolled in, I could have at most 2, 3 or 4 relations going to a particular course. and the course has a field of the students that are enrolled in, that points to me.
Yeah, but how do you want to create that table then? So for like you, what's your name?
Manav.
So for you, are you planning to have one row in the student table representing you, or are you planning to have many rows? Each corresponds to one course enrollment.
Many enrollments, but they all stay.
But this one row, right? So that creates a problem because that will be, in database systems, you'll learn more about this in week 8. That is a very denormalized database. Because in databases, what we want is we want one cell to contain one atomic value. So it is generally not a very good, idea for us to have a concatenation of values in one field because it is very, because it creates problems. First of all, storing them is a problem. Second of all, updating them is a problem. So as you can imagine, and updating these things, if you drop a course, if you drop a course, if you add a course, then updating them will be very difficult because you need to go to that specific field, and then you need to do some extra text processing. So that's the reason why we don't do that. But I'm glad you asked that question because that clears up why we need a new table for many-to-many relationship. In this way, this way, we'll have a normalized relational database where every cell, so basically every cell is the cell in the Excel spreadsheet. Every cell stores one atomic unit of information. So we don't store a concatenation of a bunch of cells. Each cell stores one piece of information. So and then that is the best way for querying and updating and deleting and things of that nature. So let's get back to this enrollment table. So for primary key, we're grabbing the primary keys of both participating enrollments. And for foreign key, we need to make a note that student is actually taken from somewhere else. Student is actually referencing student's CID. And then code and terms are exactly this code and term in the course table, which is course's primary key. So whenever you see syntax like this, a foreign key always references the primary key of another table. So it cannot reference student's age. So that's not allowed here. So after references, this is always followed by the primary key of that referenced table. And it's done in this way for a good reason. And in the end, we want to add some constraints to the relationship attributes, and this is the easy part. So for grade, we want to impose that grade is one of these values, and they are mutually exclusive. And maybe marks, we haven't added constraint here, so maybe we can check mark is between 0 and 100 like we did in the previous example. And this is the final schema. And so this is the data definition language you should learn in this week. And one thing about data definition language is that you need to learn it with the other operations as well, because otherwise there's no way for us to test whether the schema is great or not. Yeah. What?
So just to clarify, would we avoid multi-valued, like objects and cells as well? Like let's say students have like a favorite color. So would we have color as a different entity, and then each student likes this color, each student likes that color, or would we have favorite colors as a multi-valued thing in the students table?
That's a very good question. So in the AR diagram, let me see if we can find one with multi-value attributes. So the answer is, so maybe let's just pretend this is a double oval and this is no, this is an entity relation. And let's just pretend this is a double oval, and you're saying favorite color or favorite color. Yeah, favorite color. Your favorite color could be multiple, could be 3 different colors. And what we're saying is that whenever we see a multi-value attribute modeled in ER diagram, when we are mapping it into SQL, we need to create a new table for it. And then in that table, just like we don't have one cell containing different colors, just like we don't have one cell containing different courses, we wouldn't have one cell containing different colors. So we'll have different rows. So Jerry, so this will be a favorite color table, and then Jerry, so the first row, Jerry blue, second row, Jerry red, third row, Jerry green, and then fourth row, Alice red. So that's the way we represent multi-value attributes. And if you think about it, multi-value attribute is kind of like many-to-many relationship, but what's the difference? Like, I'm just going to ask you now. So when you think about it, after you mapping them, because a multi-value attribute is kind of like a many-to-many relationship because it is storing the interaction between 2 sets of entities. So people and colors. We have many people and many colors, and then every time you like a color, it is one row in that table. But and this is kind of like the many-to-many relationship, right? Kind of like student enrollment, like many students, many courses. Every time you interact with the course, it is a new row in the enrollment table. And now what's the difference? When do we model it as multi-value attribute, and when do we choose to model it as a man-to-man relationship? So what is specific about relationships that multi-valued attributes don't have? Let me see. So this is an example. This is an enrollment table. We have marks and grades. And do we have that in multi-value attributes? No, because multi-value attribute is already an attribute. Unless you want to say we have an attribute about attribute, then it doesn't make sense. So when do we model something as a man-to-man relationship? Well, we model it when there is specific relationship-specific attribute that we want to query, we want to ask. So for enrollment, a lot of times we want to ask, for this student enrolling in this course, what is his mark? Like how did he do in this course? In this case, we can model it as man-to-many, and then we can attach 2 relationship-specific attributes here. And for favorite color, unless you want to make the case about how much you like this color, you can score it from 1 to 10, and then that score becomes a relationship-specific attribute. And in that case, you can make the case where you have a many-to-many relationship between people and color, and then the relationship-specific attribute becomes how much you like this color. Like, I rate red 9, I rate blue 8. So if you don't feel the need to rate your favorite colors, then you can just go ahead and store them as a multi-value attribute. And if you want to describe this relationship, you want to describe the student's enrollment in this course using marks and grades, then in that case, you want to model it as a man-to-man relationship. And inherently, especially after you map them to SQL, inherently they're kind of the same. Yeah.
So in this case, is the color an attribute or an entity if I want to describe how much I like this?
Yeah, if you want to describe how much you like this color. I think that's a very weird saying. Let's just say this, you want to describe how much you like different kinds of food. Chinese food, Italian food. You rate Chinese food. How much would you rate Chinese food?
Because this is kind of many-to-many, but
Yeah, it's kind of like man-to-many where you have people on the left-hand side and cuisine on the right-hand side, and then the diamond, the man-to-man relationship is just likes. and then you have many to many, and then you have a small attribute called rating. So you like Italian food, you gave it a rating of 9, and then you also like Chinese food, you gave it a rating of 8.5. So in the end, it will be a giant table, just like the student enrollment.
So in this case, the design is like more like a
Yeah, exactly. Yeah, exactly. So if you model it as a multi-valued attribute, it will just be an attribute of people. But if you really want to store the rating of each cuisine, in that case, the cuisine itself becomes an entity. And we're describing the relationship between people and the cuisine. Yeah, that's good. That's a very good question. Okay, it's a good place to stop. Let's take a break for 10 minutes and we'll come back to more examples and maybe a live coding session. All right, let's get back to the lecture. So we've seen a couple of examples, and now let's kind of summarize what we should do whenever we see each type of notation on ER diagram. So in here you can see that this is an ER model, and this is what is called the relational data model. So in the postgraduate level course, we ask them to convert ER model to relational data model and then convert that into SQL. So basically, these are the three data models we teach in the course. And because this course is a more practical-based course, so you don't have to worry too much about relational data model. It's basically a drawing of the SQL implementation. So basically, for each table you create, you put the table header here so that later on you know which tables create. So for strong entities, you create a table for it, and then you need to underline. In here, it is colored. Usually, you need to underline the primary keys. And this is the SQL equivalent, which is more important to you than this relational data model. So basically, you need to create the table with all of the attributes, and this is the most important part. You need to specify that this is the primary key. And note that we specify the primary key in the end. You can also specify it right after. But I think usually this style is more neat because it lists all of the attributes, and then it lists the primary key constraints as well as the foreign key constraints. And for weak entities, this is a very important one. So weak entities, how do we model them? So weak entities are kind of like, weak entities depend on a strong owner entity to survive in the database. And the reason why it is called a weak entity is because it is the only entity that does not have its own primary key. It has something called a partial key. So the primary key of a weak entity is the primary key of the owner entity concatenated with its partial key. So last time we gave an example of employee and its dependent. So basically employee and its contact is the same. So for each employee, we may have different contacts. And the contacts are not important enough for us to create a new table, for us to make it a strong entity. So the way we do it is that we assign a partial key to it, and then we use the combination of the primary key of the strong entity as well as the partial key to make the primary key of the weak entity. What it means is that we may have different contacts of the same name. So let's say I'm an employee, so my name is Jerry, and I have a social security number. I have contacts Alice and Bob, and that's good. And then Nicole is another employee. She also has two contacts, Alice and Bob. So Alice and Bob are not unique in this database because it's just a partial key. The way we uniquely identify contacts is by combining the primary key of me with the contact name. So we need to specify that this is Jerry's Alice, this is Jerry's Bob, in order to uniquely identify that role for this weak entity. And the way we map weak entity is, if you just forget about whether this is weak or strong entities, if you look at this relationship, how would you model it? So this is obviously a one-to-many relationship, and it has total participation on the many side. So how, like, in many one-to-many relationship, how do we store this information? How do we store this one-to-many relationship? We just store the primary key on the many side, right? So basically, we ask every contact to store the social security number of employee. And the difference between the difference between weak entities and one-to-many relationship between two strong entities is that for weak entity, the primary key here is different. So if this were like two strong entities and this is one-to-many relationship, and then this is the name, then for contact, and then for contact table, we only need to specify name as the primary key because name is its own unique identifier. But in this case, this is a weak entity, so we need to grab social security number and the partial key. And together, they make the primary key of this contact table. And this is how it turns out. So for employee table, it's not affected because this is a one-to-many relationship. For contact, we need to store the owner employee's social security number. So that's a foreign key. So we need to store social security number, or that comes from employee's social security number. And then this is very important. The primary key is owner's PK combined with weak entity's partial key. So basically, social security number combined with name. So this is the most important part for weak entity. We create a new table for it, and then the primary key is the owner key plus partial key. Yes? Is it possible for weak entities to have end-to-end relationships? Well, it cannot. So it cannot have end-to-end relationship with other strong entities. So these relationships only exist between strong entities. So basically, it's not a real entity, you can say, and it needs to depend on the owner entity, and this is the only relationship it can be in, and it is called the identifying relationship. Yeah.
When we write primary key, SSN, name.
Yeah.
Do we mean that each individual element must be unique? Must be a primary key, or that the pair is a primary key?
So when we write it together, it means that for the contact table, the combination is a primary key. So in this table, what it means to be a primary key, it means that each row can be uniquely identified by that combination of values. So to uniquely identify a row in contact, you need to know the social security number of the employee, and then you need to know the contact name. And in this case, I think what you're trying to say is that in the owner entities table, social security number is the primary key, which is uniquely identifying those rows. And for contact, you need to combine them to be a unique identifier. Yep. So basically create a new table for it and make sure that the primary keys are modeled as the combination of them. So this is the most important part. M2M relationship, this is not new. We have done this many, many times. So two entities, one relationship in the middle, create two tables for the entities, and then we create a third table as a cross-reference table for the relationship. And the good thing about end-to-end relationship, you can see that we can actually add more attributes to the relationship. So if it were a multi-valued attribute or something like that, then we only have these two fields. So for many-to-many relationship, in the relationship table, we can add on more relationship-specific attributes. So in this case, when is the last time the customer owned this account? So obviously, this information is important to the bank. And the SQL implementation is easy, so two tables. And third table is the most difficult part, where the primary key, you need to specify the combination of the two primary keys of customer and account becomes the primary key of owns. And then we need to explain where are these coming from. So account number is actually coming from accounts table account number, and then customer number is actually the customer number from customer table. And one-to-n relationship, this is easy. This is a one-to-many relationship. We identify the one side, we identify the many side, and then we ask the entities on the many side to store the primary keys of the one side. So each branch corresponds to many customers. So for each customer, we store which branch you're with. So obviously for me, my bank is with Kingsford branch, and for you, your branch is CBD branch. And one-to-one relationship, so this can be interesting. And when we have like a one-to-one relationship, do we need to create a new table? No, because we didn't even create a new table for one-to-many, so why do we bother creating a new table for one-to-one? And for one-to-one, obviously, so looks, for instance, for manager and branch, what it means that manager has total participation. So a manager manages exactly one branch, but some branches are not managed by anyone. It can branch has total or partial participation, which means that a branch can be managed by 0 or 1 manager. So a branch could be, unmanaged. And when we are storing the foreign keys to represent this managing relationship, there are two options. We can store the branch number in manager's table, or we can store manager's employee number in the branch table. So which do you think we should do? I mean, the answer is already here, but it's good to think about it. Pardon? We're storing the branch number in manager table. Why?
Because manager, it requires the total participation. So it's not now.
Yeah, so that's a good point. So you're saying that manager has total participation. So what if the other way around? What if we get rid of that, and then in here we say for each branch stores the manager employment number. So what will happen?
Some will be empty.
Yeah, some of them will be empty. Yeah, so from one-to-many relationship, this is the tricky part. Obviously, we could do both, but usually we do it on the side that has total participation. So if this were like one-to-one relationship where both sides are partial participation, then it doesn't matter where you put the foreign key. But since manager has total participation in this case, whereas branch has partial participation, if we put the foreign key on branch side, then basically we're asking each branch, hey, just in case you're managed by somebody, provide that employee number. But sometimes, as you can see, that the branches are not managed by anyone. So that field becomes empty. So that is something we don't want in the database. Like, it makes the database not normal. And that's something that we don't want. We want to avoid null values as much as possible. And in this case, this is fairly easy. So for two tables, and then we pick the table with total participation. In this case, manager has total participation, and we need to store the manager. We need to store the branch number it manages. So to begin with, we have two tables. To reflect that one-to-one relationship, we add that branch number to the manager. Okay, and sometimes there is an n-way relationship. So n-way relationships, we don't really handle them, but we don't really talk about them, and you don't really worry about that too much. And we're going to give you an example of how it is usually handled. So let's just say that this is a prescription, and then now this diamond has three hands. It has a doctor hand, drug hand, and patient hand. So in order to describe this prescribes relationship, we need to involve three entities, the doctors, drug, and patient. And the way we usually handle many like three-way relationships, so this is a three-way relationship. The way we handle n-way relationship where n is larger than 2 is that we make the relationship an entity, and then we make two-way relationships among other entities. So basically, we make prescribes its own entity, and then the date and quantity becomes its the date and quantity can become its entity-specific attributes, and then for prescribes and doctor, for prescribed and prescription and doctor, prescription and patient, prescription and drug, we create three separate relationships, and then we think about whether they are total participation or partial participation individually. So this is how it is usually done. You don't have to do that in your assignment, and if you do that, if this is actually ever brought up, we'll do this for you. So you will never encounter an n-way relationship. So we just want to know how it is usually handled. So we put the original strong entities for doctor, patient, and drug. We create tables for them, obviously. They should have their own primary keys, obviously. And then we make the n-way relationship a new strong entity. And then in this strong entity, we need to look at the relationships between this strong entity with other entities. So doctors makes prescriptions. This is 1 to n. Prescription is for patients, 1 to many. In this case, we don't need to create new tables for them, so we just add the foreign keys here. And in the end, there is a many-to-many relationship. We do create a table there. So basically, just in case in the future you need to do that, just make the relationship a new strong entity and then work out the rest. And then just treat them as two-way relationships that we talked about. So basically, we're reducing the case to many two-way relationships. And another thing that's important is composite attributes. Composite attributes, we talked about them, I think on Monday, last week we talked about composite attribute. Composite attribute are usually a design choice in ER diagrams, and sooner or later we need to collapse it. So for instance, for address, it has name, it has number, street, suburb, and postcode. And for people's name, we could separate it into given name and family name. And it's the same reason we don't put a bunch of we don't ever put a list into a cell. So if you put a list of values in a cell, that's usually not a very good idea in relational database. So what we do is that there are two ways of handling composite attributes. As you can see, that the attributes now have like a hierarchy. So the two ways of doing it, the first way is concatenation. So we just concatenate all of the attributes together and make it a string literal. So for address, we just treat it as one string, one giant string. And later on, we can process them in using string-related syntax, something like that. So option 1 is concatenation. So now all of the names become just one field, name. And then you put first name and last name in the same field. And option 2 is flattening. So you can flatten out the composite attribute into individual attributes. So for address, we get rid of address attribute and we keep number, street, suburb, and postcode. So now we have like 4 new attributes. Okay, so that's fairly easy. So if you want to concatenate, just do one field. If you want to, if each of the field is very important to you, like you really want to query based on a suburb, based on street, then maybe it's a better idea to break them into individual components. But this is the important part that we talked about briefly in the first half of this lecture. What do we do with multi-value attributes? So favorite colors. So person can have different favorite colors. And the way we map multi-value attributes is that we create a new table for it. and then in that table, the primary key will be the primary key of the owner entity, as well as the attribute, as well as the actual multi-value attribute. So in here, the multi-value attribute is favorite colors. You could have like a bunch of them. And then this is the original person table that you are going to create anyways. And you're going to create anyways. And for favorite color, you create a new table for it. And then in that table, the owner entity's primary key is kept as part of the primary key, and the color is another part of the primary key. So basically, in favorite color, SSN and color together is a unique identifier of this new table. So basically, in that table, you expect Jerry red, Jerry blue, Jerry brown, and then you have Alice red, Alice blue, Alice brown. So you need both pieces of information together to uniquely identify a field. So in this table, it's kind of weird because the key attributes are the only attributes here. We don't have any other attributes in here. So if we really want to put more attributes in here, then maybe in the beginning, we don't model it as a multi-value attribute, and we just model it as a many-to-many relationship. And then on the relationship, we can have more relationship-specific attributes. Okay, so to sum up, the tricky parts are with weak entities as well as multi-value attributes, and I recommend you to work that out at home. Really think about how it's mapped and maybe create some toy databases in VXDB02, and then and really look at what are the unique identifiers for each table. So the unique identifiers for each table is very important. And lastly, we need to talk about how to map subclasses. So we talked about subclasses last time. So basically, we could define a new strong entity based on an existing strong entity. So in this case, employee can inherit the attributes from person, and manager can inherit attributes from both person and employee. So in this case, the subclass, each entity only have one subclass, and it's very easy to model that. So there are three types of modeling as usually done, and it really depends on, usually it really depends on the type of query you run on them. And so for ER style mapping, what you do is that you create the parent class tables, and then for each of the subclass table, you don't add the attributes of the parent class. So for instance, this is an ER style mapping. So for person, we create a table, social security number, name, and address. So all of these things. And then for employee, because it inherits from person, so employee's primary key is still social security number. So we need to keep the primary key here. So employee has primary key, but entity relationship style mapping, we don't specify, we don't put the attributes of the parent class, we just put the subclass specific attributes. So for employees, we're more interested in his salary and position. And then for manager, we also keep the social security number, which is the primary key in person's table. And then for manager, we only keep the bonus attribute. So this is the ER style mapping. And for object-oriented mapping, for each table, we need to keep all of the attributes related to this table. So as you can see, that this is kind of a design choice, right? For instance, if you really want to know if in your database, in your application, if a lot of times you want to know where does this employee live and where does this manager live, then obviously the object-oriented mapping is better for you because it keeps these attributes within the table. So you can basically query on this table and say, select from manager where social security number is blah, 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 and salary larger than 10,000, and then select the address from these managers. But whereas in ER style mapping, it is more efficient because we're not storing redundant information. However, if you want to know what is the name of the manager, so that's a very simple query. What's the name of the manager? What's the name of the employee? You ended up having to join the table with the parent class table to get that very simple information. So for manager, we want to know the name. The name is not there. We can join that back to persons table by matching the social security number, and then we'll get the name. So it's completely a different design choice. And also in the end, we have a single table with nulls mapping. So if querying is very, very important, yeah.
Why is it like employee and manager a weak entity?
Um,
Rely on the person's entity.
You mean why they are not weak entities or why they are weak entities?
Well, why they're not?
They could be weak entities, but in this case, we want to make, so this is, I think this is a good question, but in this case, this is just their design choice. This is an example of how subclasses are mapped, and maybe in their business logic, it is better to have employees and managers have strong entities, because strong entities can have relationships with other strong entities. So we can draw more one-to-many, many-to-many relationships between strong entities. And for context and dependence, they're not like super. This is like from my guessing from the database. This is not 100%. This is not 100% accurate because it depends on how you design your database. You can definitely make the employee. You can definitely make the. Wait, now that I think about it, you cannot make employee a weak entity of person because employee is a person. So the reason why we model it as subclass is because employee is a special type of person, and then manager is a special type of employee. So in these cases, we model them as subclasses, and they're still strong entities. Whereas in the weak entity case, in the weak entity, let me grab the weak entity. In the weak entity case, the contact and employees are different people. So employees are like, they're hired by the company, and contacts are basically maybe their clients. So in this case, they're different things, and then contacts depend on employees, but they're not employees, whereas in the subclass example, employees and managers are special cases of people. So that's why we model them as subclasses. That's a good question. And here we're only looking at how to map them when we have one subclass. And the last style of mapping is single table with nulls mapping. And I think I talked about, we don't like nulls in relational database because it drives us crazy. Like, I think, have anybody played with pandas in Python? Like, have you ever done like a data analytics task where there are nulls you need to fill? So it's super annoying. You need to decide, what do we do with the nulls? Do we fill them with zeros, or do we fill them with average number? Do we fill them with medium number? Like, it drives data scientists crazy. So most of the times we don't like nulls, but sometimes we want to keep it this way, where we can have a giant table and then we can leave it null for certain fields. And when do you think we want to do that instead of, doing this? I think it goes back to our discussion about the application requirements what queries will run on the database that drives our database design. So when do you think, what kind of query is asked a lot to make this design make sense? So when do we want to design it like this? Is it designed for storage or is it designed for querying? So I think he mentioned a good point in the last class where why didn't we create a new table for one-to-many relationship? And if we do, what would be the benefit? Well, if we do create a new table for one-to-many relationship, then we have that table readily available. And then when we want to ask questions like what manager manages this specific branch, we can easily just query that table and then get the result. And in relational databases, joining tables takes a lot of time. I think you'll learn more about that in a couple of weeks. So if we could have like one giant table storing everything, in essence, it makes querying a lot faster. So that is the motivation behind single table with nulls design. So when we have single tables, as you can see that everything is stored in this giant table. We have social security number, name, address, salary, position, and bonus. Doesn't matter whether you're an employee or not. Doesn't matter whether you're a manager or not. Just in case you're a manager, it puts bonus there. So most people don't have bonuses, but just in case you're a manager, they put bonus there to make querying, to make searching faster. So if we don't have this single table, what ended up happening is you need to join these tables with the parent table to get this information. So now we have one giant table, then querying is much faster, but now we have to put up with these null values. So this becomes a trade-off. And another type of subclass is where we have more than one subclass, as we have looked at last week. So what if employee has two types, permanent and casual, and how do we map them? Well, so this is an example of mapping them. Just look at how it's done. So we're going to focus on the ER style mapping most of the times. So we create a table for the superclass. So the superclass is employee. We put employee ID, name, and address over there. So that's the superclass. And then we create two tables for the subclasses, for permanent one as well as for casual ones. So for these ones, we need to keep the employment ID field because it is the primary key of the parent class. So the way inheritance in subclasses work is that they all have the same primary key. So that's what we can kind of treat them like the same entity with different variants. So they're all employees. So their primary key is always the employee's ID. Yes?
How do we know employee is the superclass?
Because that's a good question. So based on the ER diagram, so the D, the circle, that's the notation for connecting superclass and subclasses. And when we have a thick line over there, it means that it's total participation of this subclass, which means that the employees are strictly divided into permanent and casual roles. And distinct means that you are either a permanent role or casual role exclusively. So that's a notation of superclass and subclasses. And so basically create a table for employee, superclass, and then for permanent and casual roles, we create tables for them as well. But we also keep the primary key of the superclass. So for permanent, we keep the primary key, and then we'll need to mention that this is actually referencing employee's primary key. And then for casual, we need to create a its own primary key, and this primary key is actually referencing the superclass primary key. So I'm glad you asked that question, because by looking at this subclass, by looking at the participation constraints as well as the disjoint constraints over here, do you think these constraints are reflected in the schema? Do you have like one? Okay. Okay. Just by looking at these, do you think the participation constraints and the mutually exclusive constraints are mentioned in the schema? Looks like there's no way for us to enforce it here. Like at least it's not enforced in our current implementation, because here we are saying that the employee needs to be either permanent or casual. But in this case, it doesn't prevent us from having some employees that are maybe part-time, that are who don't have any, who are not permanent or casual. So if we have like a table, if we have an entry in employees table that does not specify the permanent or casual, then this total participation constraint is broken. So right now it is more like a partial participation, as well as for this distinct constraint. Usually what needs to be, right now it doesn't really specify permanent and casual are mutually exclusive. We could have a table, we could have a person who is both permanent and casual in these tables. So that is why subclasses are very hard to, sometimes they're very hard to implement these constraints in the at the database level, and a lot of times we need to enforce these constraints at the application level. So one example that we can do here is that we still can enforce at the database level is that we can have a discriminator column in the superclass table, and then have that column to take after values in either permanent or casual. And in that case, we're enforcing that those two subclasses are mutually exclusive. So that's a very hard thing to do, and for total participation constraints, it's even harder to enforce that. So usually for subclasses, we leave it like this, and we'll enforce the rest of the constraints at application level. Okay, so that's test our knowledge and build a small library database from scratch. So this is kind of like a toy version of the practical 2 exercise. Okay, I'm gonna go to my own. Okay, so what we want to do here is we want to create a database called a library, and we're going to play with a very simple scenario where we have libraries, we have members, and members can borrow books. So first we need to create a.
If we only add one column, so if it's not sufficient.
Pardon?
If you only add one column in the.
You mean the subclass scenario, right? You mean the subclass
Yes.
modeling? Yeah.
Add one column in the superclass.
Mm-hmm.
If the case is partial participation.
Yeah, partial participation.
No, the
To-
case is
Total participation, you mean?
not disjoint. So how do we store the information that I'm both casual or permanent?
That's a very good question. So I'm not sure you guys understood her question. So she's saying that if the case here is, right now the case is disjoint, right? It's disjoint. And we can use an extra discriminator column in the parent class and then say employee type in a couple of values. And in this case, the employee types are mutually exclusive. And what she is saying that, what if the employee type is not mutually exclusive? That you could be both a part-time and a casual. And in that case, so that's a good question. In that case, it's very hard for database level implementations to enforce that constraint, we need to move to application level constraints. So basically, when you're basically in Python, we can enforce that. So.
Do like columns of permanent and casual and just do like a true or false for the
If you do, but there will be like, if you, right now we only have like 2 subclasses, right? So there are like 3 scenarios, 0, one of them, both. But if you have like more subclasses, then those true or false becomes very, very complex. Like you could have like, in theory, you could have 2 to the n combinations of those subclasses, and then it's very hard for the parent class to keep up with that. So it becomes a disaster in schema modeling. So basically, in the superclass, it's very hard for us to make those switches, as you say, the switches for different, to accommodate overlapping, many overlapping subclasses. So so my point is, this is a very difficult thing to do, and usually it is better done at the application level. Okay, let's quickly get through this example, which should be fairly easy, and it is kind of like the practical 2 exercise. So, so basically, we'll create a book table for each book. We'll have an ID, the title, and we need to have the year, and the primary key is the book ID. And then for member table, the primary key is another ID. So in real life, we a lot of times we just throw an integer to it and call it an ID, and then be with it. And then for the borrowing table, so this is a man-to-man relationship. We create the primary key by grabbing the primary keys from both tables, and then for foreign key, the member ID is referencing the primary key in member, the book ID is referencing the primary key in book, and that's pretty much it. And after that, we will start to, so this is part of the data manipulation language. So after you design the database, you need to start insert the values in it, and as you insert the values, you will see that whether this tuple is getting accepted or not. So if it satisfies the, wait, this is, I didn't know you can touch that. If the values satisfy the constraints you have defined, then they get accepted. And if they violate constraints that you've defined, then it will be rejected. So let's take a look of that. And I've already sourced the M file, so I need to create start the database. Let me see if I created list of library database. Okay, let me drop that real quick to do it from scratch. Is this big enough? Should be big enough. Okay, let me create the library database. Just call it lib. And right now I have a bunch of files prepared because I don't like typing in this interface. It's a disaster to type here. So basically, the schema is here. You can see that this is the book table, this is the member table, this is the born table. All of these constraints will be useful when we are inserting those values, when we are inserting those tuples. And data SQL, these are the good data that we'll insert into the database. And if you look at these will be some bad data that we are planning to insert into the database that, so basically we could borrow a book that does not exist. We could borrow a book with no title. We can start to insert a book with a very weird published year. And we can do all this sort of stuff to test the validity of our schema. So I'm going to do everything from the database. So when you see something like this, then you're in the SQL database. So right now, we don't have any relations and \I to execute a SQL script in your current, in a defined directory. So right now it's in my current directory, so I can easily run schema.sql from here. But if you want to run it from, like, for instance, CS3311, a weird folder, you can also do that. So if you do that, it creates 3 tables for us, and then that's investigate each table. Okay, I hate typing in here. Tab don't work. Book. So if the schema is correctly created, then you can actually see the constraints that are enforced here, and then the primary keys as well as the foreign keys that are enforced here. And this is very particularly interesting. For each primary key, it creates an index for you. So this will be very, you'll understand more about this in the later part of the course, but I'll probably give you a demonstration of what an index is as well. And what other tables we got? A member table, and we got a borrow table. Do you have borrow table? Borrowing table, okay, borrowing table, okay. So let's take a look at those from books. So select everything from book, nothing, because right now these tables are empty. Nothing and borrowing, nothing. So right now these tables are empty, so we need to populate them with the real data. So run the data SQL. In the data SQL I have shown you. So data SQL is basically a list of insert statements. So what it does is that it will run each of these statements one by one, and it will insert into these tables. And the order in which you insert into these tables matter. Right now we're inserting books first, members, and then borrowing. If we insert borrowing first, it could create a big problem. So we're going to show that. So right now, everything is fine. And because the schema is well-defined, we have enforced all constraints there. So if we actually try to break it, it will give us all kinds of constraints. So I recommend you read all of these complaints and then compare them to the bad data we're trying to put in there. So maybe it's better if we look at from here. So this is another way, just in case you don't know, this is another way you can run SQL queries. So PSQL database name, file name, and then let's just look at the head of the data, the bad data. So the bad data starts with inserting into borrowing values 1/99/2026, February 10th. And why did it break? Well, here it says that it violates a foreign key constraints, borrowing ID foreign key. So basically, we're borrowing a book that does not exist. So borrowing value is 1/99. So let's go investigate that database. So we don't have that book here. So for books, we have 1 and 2, but it's trying to borrow the book 99. So that would be a violation of foreign key constraints. And if you look at all these things, it violates the different types of constraints, and try to map these to the bad data and really understand why each of them is bad. And let me show you something else that is very interesting that probably is out of scope for week 2, but is very interesting. So remember when we said primary keys are super important? Why don't we just create a column and then say unique and not null? If we just enforce it is unique and not null, Is that the same as declaring that it is primary key? When you declare something as a primary key here, we create a index for it. So basically, it's kind of like for a book, we have a catalog. So if you want to find a specific chapter information about a book, you have to go through the whole book to find that information. But if you have a catalog, you can read the tag catalog, and it will give you a pointer to where you want to go. So let's just say that, let's just run this real quick. So these are all of the borrowing. So what if I specify that I want to find the rows where the member ID is 1. Let me see how the database is actually absorbing this thing. So as you can see that this is probably too advanced at this moment, but it's using a heap scan as an index scan to look at the database, which means that it is actually using the index that we created on a table. So if you're querying on a different field that is not a primary key, it is likely it will need to go through the whole book to find that information. So let's look at maybe member. For member, the name is basically a very ordinary field that is not a primary key. So let me see what member are there. Member. So Alice, let's just look at Alice. So if we do a query, so basically it's playing tells us what is going through his head. So if we're selecting from this table by specifying the primary key, what it does is that it will use an index scan. So basically it uses the index it created to make the query faster. What if we do name? What if we just say where the name is Alice? It will do a sequential scan on the whole table. So right now, we only have 2 rows in the table, so it doesn't make a huge difference whether you look at the whole table or you use this index to pinpoint where the data is. But when the data is huge, this makes a huge difference, as you can see. So basically, index gives you probably constant query time, whereas sequential scan gives you like big O-N linear query time. So I'm doing this demonstration to show you why primary keys are important, and you understand more about this in later part of the course. Okay, that's it for today's lecture, and on Thursday we'll talk more about the database we use in assignments, and we'll probably release assignments on Friday. Hello.
I have a question. I'm not on the discourse.
Oh.
Yeah, it kind of just goes white.
You're not on discourse? Okay. Can you send an email? Can you post it on the forum? If they don't reply you by the end of the day, send us an email.
On the forum where?
Oh, sorry. The discourse forum. Yeah. Send us an email. Send us an email. To CS2311's email. Yeah.
For the primary key thing that you were saying, that there's an ID that it's form. How does the ID what is the basis of the ID's form?
Oh, the ID. You just make it. You just declare a new field called ID and then declare it as a primary key. So basically, you just create a new field.
I just say that it's primary key as in the create table portion. I just say that this particular column is the primary key. You put it that way, right? So
Yeah.
who creates the ID? Is it like the system making the ID?
You need to make the ID. You need to specify ID and then maybe integer, and then in the end you need to say primary key ID, so that the database knows that this field is the primary key of the table.
But can't it like do something else, like maybe putting in the IDs as the ID or something like that? But you showed the ID scan, right?
Pardon?
You showed the ID scan, right? Like the scanning for primary keys done differently, an ID scan instead of a sequential scan and stuff like that.
Yeah, we need
Yeah.
to depend on
Yeah,
primary
so, like-
keys to do that.
Yeah, so like, how do we get that ID? Like, how does the scanning happen?
So this is created. So the index is created for you by the database. So if you declare some value as an index as a primary key,
Yeah.
underneath it will automatically create an index for you. You don't have to do that. So if you would do
Yeah,
that
I'm
for
just
you,
asking for curiosity, like how does the ID get created for that thing?
how does the
Like
ID create?
their background ID that they're creating, like how do
You mean how you create or how they?
how they do it?
How they do it? They use a B tree. They use a B tree. It's kind of B tree is kind of like a multi-dimensional binary tree.
Yeah.
So where you can sort information in different fields. Where in binary tree you're sorting things in one dimension, right? And in B tree you're sorting things in multiple dimensions. You can sort them, and when you have sorted them, you can easily find them. So everything is sorted in an index. Okay, you can go look at B tree or B plus tree to understand it. Yeah, one. Can move it over there. I think they're setting up.